Hello and welcome to the next session in the PML School. This will be from the Gabrielsson and Weiner text, exercise PD12, modeling inhibition of enzyme activity by means of turnover. So a bit about the background here. In the study background, and this is a study conducted in mice that produce excess human amyloid precursor protein. The cleavage of APP initiates a cascade of secretases, including gamma secretase, that results in the formation of amyloid peptide fragments that deposit to form insoluble plaques in the brain. By inhibiting gamma secretase, one hopes to produce less plaque formation by a decrease in formation of the amyloid peptide fragments. The concentration of soluble beta amyloid in the brain serves as a biomarker of gamma secretase enzyme activity. Okay, so in this case, we want to characterize the turnover-driven response to a gamma secretase inhibitor in mice. The response is measured as % decrease in the biomarker beta amyloid versus time. And here we have the exploratory plot where we see % inhibition on the y-axis and then time on the x-axis. So we see an onset of the response within the first 1 to 2 minutes, and then an offset of the response after 4 minutes. Okay. So in the protocol, previous studies show a delay between the peak inhibitor concentration and the maximum inhibitory response. So here is an overlay plot where the left y-axis is the concentration, and the red smooth curve is the concentration plot versus time. The right y-axis is the gamma secretase inhibition versus time. And we see that the peak plasma concentration is occurring in about 1/2 of a minute, whereas the peak response is occurring at 4 minutes. Okay, so this type of profile suggests an indirect response model. For this compound, the PK is well characterized. So we have good PK parameter estimates from prior fitting. And what we're going to do to get concentrations for the PD study is use fixed parameters from a one-compartment model obtained from the previous study to simulate the concentrations. So this is going to be an extravascular one-compartment model where the concentration function has an absorption rate constant of 8.8 per hour, the elimination rate constant of 0.605 per hour, a volume of distribution of 3.05 liters. And what we can do in the simulation is solve the concentration function at different time points for different dose levels. Okay. In terms of the pharmacodynamics, the aim here is to construct a mechanistic turnover model. What does this mean? Well, the base turnover model actually uses this response block here, where you have a K in and a K out. So this is the base turnover model. Okay, so the K in is the rate, zero order rate of production, and the K out is a first order rate of loss of response. Okay, so we're modeling the response here. And since we want a drug mechanism of action, that's going to be modeled by this inhibitory function, I of C, mechanistic. And in this case, what we're doing is we're inhibiting the production, the K in. So the inhibitory function acts on K in to inhibit it. So our I of C is a typical inhibitory Imax function, where I of C equals 1 minus Imax times concentration to the gamma, divided by IC50 to the gamma plus concentration to the gamma. So the concentration is driving the inhibition function, which then inhibits the rate of production in the indirect model. So when we get the full model, substituting in the mechanistic inhibition function, we have the change in response versus time equals Kn times the inhibitory function minus K out, which is the first order loss, times the response. And the aim is to get final estimates for the following parameters, where our Kn is zero order rate of production, K out first order loss, Imax is the maximum inhibition, IC50, the concentration at which 50% of Imax occurs, and then gamma is an exponent that allows one to fit a sigmoid Imax function. Okay. So in Phoenix, there is actually a built-in model that allows one to construct these indirect response models, and that is the grouping PK indirect. So that's in the model type. And so for the PK component, we use microparameterization, extravascular input with one elimination compartment. And since the focus here is to fit the PD parameters, and we have well-characterized PK, so we're actually going to just freeze the PK with those PK parameters and focus on fitting the PD parameters. In the indirect grouping, we will select inhibition limited of buildup, and then the exponent includes the gamma in the inhibitory function. Okay. So this is the built-in mode in Phoenix to build the model. And then over to the right here, the PML statements get written automatically. Okay. In the graphical mode, this is a summary of the graphical model. So we have the PK model here on the left, a one-compartment extravascular model. And then from the concentration function, we have all of the PD parameters here in this Emax block. And then the observations are actually going to be responses. This is the indirect response model in PML code. So this is annotated. So for the PK, these are the differential equations for the one compartment model. For the indirect response model, this is similar to the slide that I showed previously. In this case, we're using E instead of R. But we have the zero order rate of production, Kn, times the inhibitory function, minus K out, which is the first order loss, times E. Our dose point, so this is an extravascular administration, it's AA. The concentration in the central compartment is the amount in the central compartment divided by the volume of distribution. And with the turnover models, we use the sequence statement. So the effect equals rate of production divided by rate of loss, Kn divided by K out. For the observations, we're using EOBS, observed effect, which equals the predicted effect plus the error epsilon term. In the text model, when one freezes parameters, as we're doing in the case of the PK parameters, we have the fixed effect listed here, and then the freeze statement right next to the parameter name indicates that this value will be fixed in the model fitting. And then the indirect response PD parameters with initial estimates are declared here. So it's these 5 parameters that we're fitting. Okay. Okay, so for initial estimates for the model, the initial estimates for IC50 will be 1. This is derived from the overlay plot at 50% inhibition. So the concentration at which you get 50% inhibition, and that happens to be 1. For the gamma exponent, the reduced model actually doesn't have an exponent. So this is just the inhibitory function without the exponentiated concentration terms. So if one doesn't know a good estimate for gamma, a good first choice is 1 from the reduced model, and then the model fitting will then adjust the gamma from there. The response at 0 equals 60. That's from the exploratory plot with the response at time 0. The K out is derived from the slope of the downswing in the exploratory plot. That's set to 1 in this case. And then we can get an initial estimate for K in using R0 times K out, which will be 60. And then our delta R is the R0 minus R min from the exploratory plot. 60 minus 20 equals 40. And we can use this delta R to get an initial estimate for Imax. So initial estimate for Imax is delta R times K out divided by Kn, which is approximately 0.67. So these are the values we will put in the initial estimates for the run, and then the model will refine those estimates during the fitting process to get final estimates. Okay. At this point, I will go ahead and switch to the Phoenix application. Okay, so Bernd, is my screen visible?
Yes, clear.
Great, thank you. Okay, so here we have the input data set from the study. So we have the time course here, and then the percent gamma secretase inhibition. And we'll use those to construct the XY plot. So I did some of the exploratory analysis prior to the demonstration here. So if one looks at the percent gamma secretase inhibition versus time, we again see this inhibitory. We see an onset of the inhibition and then an offset returning back to the baseline. Okay. From the previous PK studies, we have PK parameter estimates. And so the PK parameters are simulated, used to simulate concentrations. So in the structural model, we have a microconstant model with extravascular absorption and one elimination compartment. The dose amount is 100 micrograms per kilogram, so that's entered under the setup dosing. And then for the parameter estimates, we'll go to fixed effects and enter in the values that I presented from the slide. So those were 8.8 for Ka, 0.605 for Ke, and 3.05 for volume. And then on the Run Actions tab, one can set to simulation, okay, simulation mode, and then enter in the number of simulation points, the maximum time range, which is 12 hours, and then the Y variable, which is C. And the result of this simulation, one can initially look at a plot on the simulation plot, individual simulation, and see the PK profile plotted here. And then in the output worksheet, there is a simulation spreadsheet that has all of these simulated time points. So basically set up a sampling scheme that would give me a simulated concentration every 0.5 minutes. Okay. And then this will be useful later for the PK data. This can be used, the simulation result will then allow one to do an overlay plot that has both the PK concentrations as well as the response plotted on the same time scale here, where again the red line is the simulated concentrations, where we can see the peak concentrations and compare them to the peak effect, the peak inhibition for the response, which occurs at about 4 hours. Okay. And if one wants to go ahead and model the effect, one approach is, what I did here was to combine the worksheets from the input. This is the input that has the gamma secretase inhibition, as well as the simulated concentrations. These are merged into one worksheet. And then this worksheet is used to construct a plot of gamma secretase inhibition versus the plasma concentration. And when one plots this with this particular data set, a clockwise hysteresis is observed. So starting from the y-axis, the hysteresis moves in a clockwise fashion. So in order to model these data, what we'll need to do is use an indirect response model. Okay, so to set up my indirect response model, we'll come back to the input data set and send it to Phoenix Modeling and then Phoenix Model. And I'll call this the built-in inhibit KN. Okay. Switch off the population mode. And then for the PK, go ahead and set this to micro, extravascular, one compartment model. I need to change the model type to PK indirect. Okay, so PK indirect is the built-in grouping for the indirect response model. And in this case, we'll choose the option freeze PK. And we have inhibition in the indirect area, inhibition limited of buildup. We'll include an exponent in the gamma, and then review the PML statements to see the full model function here. Okay. In the top panel, the gamma secretase inhibition will be the observed effect. I'll enter that. And then go to the dosing panel and enter the administered dose, which is an amount, 100 at time 0. And then for the fixed effects parameters, we'll go ahead and enter in the values here. So 8.8 for Ka. Notice that these first 3 PK parameters, there's no boundaries available since they are frozen. They'll be fixed. The volume is 3.05, and the Ke 0.605. And then as discussed in the slides, we have initial estimates for Kn, which will be 60, and the Imax is 0.67. And the other parameters that we have in the model, initial estimates will be 1. Okay, at this point, I'm ready to go ahead and run the indirect response model. And go ahead and review the outputs. Start with the fitted curve. So this is the fitted observed effect, the percent inhibition versus time, where the red circles are observed, and then the green line is the fit, the curve fit. Also look at the theta output to verify that I'm getting final parameter estimates. So again, the PK parameters are fixed, and then these are the final estimates for Kn, Kout, Imax, IC50, and gamma. Okay, so this is actually an advantage in Phoenix that we have this built-in indirect response model. And I will go ahead and make a copy of this, and we'll run it in the text mode just to see how we can go over to the PML text when running the model. So we'll call this the textual inhibit Kn. And so since I made a copy here, all of my inputs thus far have been saved, including the dosing, all of the parameterization. I will simply choose the option Edit as Textual in the Options panel here, and then say Yes, at which point I can view the PML code. Okay. So here we have all of the PML statements in the text mode. Phoenix does, by default, make both structural parameters and fixed effects. And we've discussed in some other sections that you don't necessarily need the structural parameters when you're running an individual mode. So if desired, I could actually just remove these and just do fixed effects. So here are the structural parameters, and then notice in the bottom panel, I get these red warning messages because I have used terms in the equation that are not named. So all I have to do is remove the TV designation, which stands for typical value, and these warnings will disappear. Okay, so I don't need to make any modifications, but from the text mode, if I, for example, wanted to modify the main model equation here, I could do so. But in this case, in this example, we're just ready to simply run the text model. Okay. Here we have our fitted plot as well as our theta. So it's the same model in text mode, should get the same results, you know, the identical results, but it's just a different mode for interfacing with the Phoenix model object. Okay, so if there's good parameter precision, which is the case here, we got a good fit, all of the CVs are 10% or less. What we can do is run a simulation, if desired, at different dose levels. Okay, so I've actually prepared a simulation input worksheet at different dose levels. So the base study was run using a 100 milligram dose, and I want to simulate 200 and 400 to see the impact. So we'll go ahead and run the model in a simulation mode here. So notice that I have this other column, dose level, which allows me to sort and rerun the simulation. Okay, so I'm going to make a copy of my text model and paste it back into the workflow. And I'm going to call this simulate inhibit KN 100, 200, and 400. Okay. And to run the simulation, I'm going to take out my initial data set and replace it with the simulation input data set using the dose level as a sort variable. And then in this case, I want to go to the dosing and rebuild the dosing by dose level. So the amount will be 100, 200, and 400. And these are all at time 0. Even though this AA rate variable appeared, it's not going to be used in this case since it's not an infusion. This is just a one dose administration at time 0. Okay, so the parameters, fixed effects. Since I want to run a simulation from the fitting, I don't want to use the initial estimates from before. I'm actually going to take the estimates from the model fitting. So for KN, instead of 60, we'll use 123. Instead of IMAX being 0.67, it will be 0.7, which is actually close to the initial estimate. But in this case, what I can do is simply press this accept all fixed and random button and say yes. And so these are going to be the parameter values used in the simulation. Okay. At this point, I'll go to the Run Options tab and change to Simulation Mode. And the X range is 12, and my simulation variable is going to be E, capital E, for effect. Okay. And so now what I can do is simulate at different dose levels. Okay, and then to view my simulation in graphical mode, I'll go to the simulation plot, which will show the simulated response at each effect level. And there's also this simulation workbook here, which could be used to construct an overlay plot. So I'm going to actually go ahead and do that. So from the simulation result worksheet, I'll go ahead and send this to plotting and then XY plot. And then call this overlay sim at different dose levels, where we have IVAR is X, dependent variable is Y, use dose level as a grouped variable. And for the labels, the x-axis label, I'm going to call this the time, and the y-axis label GSER % inhibition. Okay. And then execute. Okay, might want to go to the quick styles and uncheck show markers and maybe increase the line weight. So the overlay plot gives a nice view of the different dose levels. And notice from the simulation, as the dose level increases, the intensity of the response, the maximum, does not increase, but the duration of the response does increase. So at the 400 milligram dose, the response lasts longer. It has a later T offset. Okay. That's the overlay plot, and that concludes the demo portion. I'd like to go ahead and switch back to the slides. Okay. So just to sort of recap what we did, we constructed the mechanistic turnover model, fit the model to the data with fixed PK parameters, and then fitted the PD parameters and got results. And at this point, I'd like to open up for the Q&A session. Bernd, do we have any questions?
Yes, we have a couple of questions, but if there are further questions, I would encourage everyone to post these at the right-hand side of the WebEx console. So we can cover a few of those. Chris, first question is if you can go back to the interface, the Phoenix model interface, where you set the options for the indirect response model. Can you explain the different options and what they mean? Yeah, sure.
So I'm just going to go ahead, since I already have modeling results, and let's go ahead and do this. I'll work in a copy to talk through the answer here. And I need to go back to the built-in mode. Okay, so in the built-in mode, there are actually four primary models in the indirect response group, and those are controlled in this indirect area. So you can get these inhibition of buildup. Okay, so that's inhibiting the Kn. You can also get stimulation limited of buildup. So in this case, you're actually stimulating the Kn. You're increasing it with an Emax function. So instead of having an Imax function with an inhibitory function, you've got a stimulatory function. You can also do stimulatory infinite. So in this case, you don't have the maximum. You don't have an Emax in this case. And you can also stimulate the loss. So you have an unmodified Kn, but in this case you have a stimulatory function that that increases the K out parameter, that acts on K out. Okay, and then you can toggle between whether or not there's an exponent, the gamma term on the concentration terms. And you can also do inverse, linear, or log linear versions of the inhibitory and the stimulatory models. Next question.
Okay, a couple of related questions here. Can we use the same model for stimulation of Kn, and can we combine both inhibition of KN and stimulation of KN?
Both inhibition and stimulation. So yeah, so in that case, you would need to write a custom model in your text model. Usually you would pick one or the other. You might have a inhibition of Kn and a stimulation of K out, for example, and you could certainly add those functions simply by multiplying them by Kn or K out. You would need to do this in the text mode. So basically, what you do is you would take this model equation here, and you might add the stimulatory function, say, to this model statement. But usually, if you're modeling both of these, you need to account for the Kn in the stimulatory case and the Kn in the inhibitory case.
Okay. Thanks, Chris. Maybe one final question. If you fix the PK parameters for your PK/PD model, do you give the simulated concentrations or real concentration as input to the indirect model?
So these are going to be the simulated concentrations. And we actually don't have any observed concentrations in this particular study. Yeah, all of the concentrations are simulated.
Okay. I guess there's maybe one question. How can you get R out initiate? I guess this means K out, right? The initial estimate for K out. But I think you had it on your slide, right?
Yeah. So the initial estimate for the K out was if we switch back to the slides. Actually, I probably could. Okay, switch back to the slides. So the initial estimate for K out is the slope of this upswing in the offset, and so just taking the slope of this linear portion and using this as the estimate of the K out.
Okay. All right. I think we can finish with the Q&A, and for any remaining questions, as usual, we'll follow up with a written response. And yeah, thanks, Chris. Yeah, if you go to the next slide, we will make available all the materials after the event on the Certara forum, as usual. So please look at the URL on our forum, and so the model text will be also available as file download, and all the questions and comments. And if you have some further questions, you can always send to our support email address at support@certara.com. Maybe just another channel that we use since recently, we have created a Twitter account at PML School, because what we realized is, we have typically only a very small bits and pieces of information that we will share with this specific community, and for this we have created this PML School Twitter account, where we post notifications on updates of materials, Q&As, and also when there are some discussions going on in the forum. So if you are interested in getting these notifications, please follow us on this Twitter account. Also, the announcement of new sessions, we see that email is doing quite a bit of an effect, but sometimes we get rebounds email messages, and maybe if you want to stay up to date with those announcements, you might want to follow us there. As you know, we've also, as you may know, we've also created a YouTube channel, a playlist for the PML School sessions. So we have uploaded right now 13 different videos, and here's the URL for watching those sessions on YouTube. Okay, next slide, please. You know, this is a PML school, and what you can think of, I mean, if you finish this school, you would be well versed in you know, trying a little bit more, getting a university degree or something like that from Certara. So this is what we offer at Certara University, a wide range of on-demand and classroom courses where you can increase your knowledge about either the software tools or also the theoretical concepts behind PK/PD modeling. So you can just visit us at the Certara University URL to look out for more information. Next slide, please. Yes. Yeah, and finally, what's coming up? I guess I've announced this last time already. We have a very interesting webinar coming up that is held by Wojciech Chrysanski, and he's going to speak about modeling PK/PD systems with distributed delays. So whenever you have kind of a lag or either in the concentration or in the response, you want to deal with distributed delays, and Wojciech is giving his expertise advice on this on the May the 16th at 11 a.m. EST. And finally, our next PML School session is in 2 weeks' time. On May 11th, I will talk about effect compartments and with IV infusion and multiple doses. So if you're interested, please sign up at the usual place, and hope to see you there. With that, I want to close this session. Thanks all for your continued interest, and you may want to disconnect now.